Okay, so our next session, technical session, preceding obviously the coffee break, is technical session 1 on different types of algorithms, new algorithms, implementing Tsetlin machines. I would be requesting Dr. Anatoly Gorbenko to please chair this session.
All right, so we're given a promise to chair the session, the first session, and then the first presenter is Dr. Tsetlin. Anatoly, I see. So the first presenter of the session is Dr. Sid Hart, who we know as Sid, and he is now working with the Indian Institute of Technology. As I understand, Sid was graduated as a bachelor from this institute and then come to Newcastle and got the master and PhD here, yeah, and then working as a researcher, and then go back to the home country, probably different city, and now he's working there as an assistant professor. So Dr. Sid, your time, and so the session is 20 minutes and then 5 minutes for discussion and questions, and I'll give you 1 minute notice when we need to finish, right?
Hello, everyone. My name is Siddharth. Thank you for the introduction. So the paper is titled Introducing Trim Automata for Settling Machines. So we are trying to introduce a new kind of automata architecture. The motivation behind is basically we want to implement a training chip, a settling machine training chip. So the idea is that the architecture is quite huge, and the most amount of area is consumed by the clauses which contain automata. So like this, and in a clause, the settling automata is the most like the fundamental element of this settling machines, and this occupies, they can be huge when implemented in, like, for example, in problem like MNIST will have 1.5 million around automata. So on a training chip, implementing them in different formats will consume a lot of chip area, which they dominate the chip area. So the idea of this was that can we propose an automata architecture which would help us reduce the area of when implemented. So we proposed three action automata. So this on the left side is the vanilla automata, which one of them representing the literal and its complement. While what we are proposing is 3 action automata, we are combining these literals together so that we can we can give simultaneous actions to them. So, for example, it can be include, which can be represented as it can. So include is not important because we cannot include both literal and its complement. But there can be 3 permissible actions, where we include the literal and exclude the complement of literal, or the vice versa, or exclude both of them. So when we to see if actually it gives us some benefits in terms of area, we implemented it using open lane, which is a ASIC chip pipeline. So when compared to this vanilla area, basically we got almost like 36% reduction in area when using 3 action automata, and almost 39% reduction in power when all of them were running at 100 megahertz frequency. So this was the motivation. This motivated us to maybe design an architecture, new kind of settling machine using 3 trim automata. So how does metastates work? In a vanilla automata, there is include and exclude decisions. But as we discussed, we are combining 2 automata together, belonging to literal and its complement. So we have 3 actions over here. One is exclude include, one is exclude, another one is exclude exclude, and the third one is include exclude. So in include exclude, basically we are including the literal but not but excluding its complement, and exclude we are not including either of them. And in exclude include, we are including the literal's complement and excluding the literal itself. And we are assuming the final condition where both are included as invalid, because settling the clause output will result in 0 anyways. The challenge was when we designed the training algorithm for this kind of automata by drawing analogy for vanilla settling machine. We encountered certain issues. for example, when we transition from, let's say, this particular decision to an include exclude decision, there is a fixed path of penalty. So it will go to include exclude, and then it will go to upon receiving another penalty, it will go to exclude include. So this fixed path of transition between different meta states was not producing good results, good training results for us. So we preliminary we thought of that maybe since it's restricting the total number of states or possible combination of states, maybe we need more stochasticity here. So we introduced certain more hyperparameters where before transitioning from between any two meta states, we were doing certain random number comparisons. Random number comparisons are a very important, crucial part of the settling machine training anyways. So we thought that maybe we should introduce more stochasticity over here. So we introduced different parameters, but however, in this paper, we have assumed all alpha 1, alpha 2, beta 1, beta 2, and gamma 1, gamma 2 to be 0.5. So 50% probability of remaining in the same meta state or transitioning from one meta state to another. So in actual implementation, it has been implemented using binary encoding method. So that means the state changes basically increment or decrements rather than gray code encoding method. So in gray code encoding, we also actually did some experiments and found that the area of automata is quite huge in the preliminary results, which I showed in this table basically. So we excluded and we just we used a binary encoding. So these are the states. So the meta state 00 will range from, let's say we have 500 states for each meta state. The number of states is 500. So this will range from 0 to 499, 500 to 999, and this thing. And then we see that if it reaches, let's say over here, if the state value is 499 and there is a penalty, so then it will go to another meta state depending on the random number comparison. So these are state transitions between different meta states. So the results, we experiment with different data sets, including MNIST, FMNIST, KMNIST. We also use CFAR2 and KWS6, but they were not, I mean, in preliminary results, they were not very accurate. So we included these three main results where we were able to actually produce very good training accuracy. Compared to, so we are comparing with the vanilla settling machines, which was proposed earlier with the name of redress. So our accuracy is almost comparable to redress's accuracy. And one contrasting feature over here is in redress, let's say we are using vanilla settling machine. So the total number of possibility of states is like 120,000 for two automata. But in this case, it's only 1,500 since we are assuming 500 states per meta state. So that's why we can see that although the number of meta states are very small, very few over here, but the training accuracy we are able to reach comparable to the redress. So I think what we found out, the most important challenge is that we need better accuracy. And for that, and also we need fewer clauses. See, the fundamental idea of proposing this was to reduce the area chip, basically. And if we end up using more clauses to achieve the same kind of accuracy, then it's counterintuitive to our objectives. So we need to improve training algorithm. We need to maybe invent a new training algorithm for 3-action automata. And maybe a different other kind of architectures need to be explored with respect to settling trim automata. Thank you. Any questions?
We have plenty of time for questions, guys. Well, maybe let me start with my question first. So, does this mean that when we introduce this new type of automata, does it mean that we need to introduce a new hyperparameter?
It's not necessarily, but when we tried with fixed transition path, it was not producing good results. Like it was saturating very quickly, and the training accuracy was not increasing anymore. So we thought that maybe since we are kind of making the automata less flexible by reducing the total number of states, maybe we need to introduce some kind of stochasticity. So it's just one experiment. It's one kind of architecture. but we can explore different methods.
Probably. Any other questions?
When we introduce a new branch in the learning automata, what I may guess is that the hardness of designing of hardware is increasing, because if we have only two branch in the learning automata, we can just increase or decrease the integer. But here we have three. Then do you have any?
So here also we are just increasing or decreasing. So if suppose the state value is, let's say, 499 and there is a penalty, so there, we will increment the value, let's say, over here by 1, and it will go to maybe some other meta state, let's say here. So it will reach 500. So it will go into a different meta state, which is 10 instead from 00.
I see.
So it's basically the same.
It basically is the same, right? There's no extra overhead. Thanks.
Other questions?
See, this is a direction that we've taken, that when we found that we've got literals and their complements. So in a way, it's a little bit like dual rail encoding here that we use here, right? So that, do you see that there are other potential ways of having multi-state machines used when we share, for example, not between the literal and its complement, but there are some other sharings potentially?
So
involved.
multiple features,
because
basically.
maybe from the point of view of multiple features, or from the point of view of clauses, because TAs are effectively intersections between literals and clauses.
So we had a discussion. There are maybe this maybe not solving our problem in classification sense, but maybe we can use this first of all for regression kind of settling machine idea, where things are things are quite different, basically, because we need to predict an approximate value. And there are other architectures which we need to explore. I mean, I think with different problem statement, we may be able to use this architecture. It depends on the kind of problem statement we are choosing. Yeah.
Because at the moment, I think we've got clauses. Let's say at least vanilla machine, we have clauses split between different classes. And maybe there is some sort of mutual exclusiveness there.
Yeah, I think maybe we can try it with coalesced settling machine and then see its accuracy results, because there is then weight matrix which will, help us balance out the loss in accuracy. This is something which we can think of. Thank you.
So the next